tutorial examining Newton's first and third laws of motion, mostly. About 5 pages, going through a few different free body diagrams and finding the interaction partners to different forces. So, good things to practice in terms of Newton's laws of motion. We have a string that is tied to a book and pulled lightly, as shown at the right. The book remains in contact with the table and does not move. That phrase, like begins and remains at rest, tells me from Newton's third law of motion, add up all of the forces acting on an object and they have to sum to 0. There's no acceleration. So the most it could do is move with a constant velocity, and since this is starting at rest on a table, that velocity is 0. Draw a free body diagram for the book. Label each of the forces exerted on the book as you were instructed in tutorial forces. Alright, so the book has weight. So there's a force of gravity acting down. The dot is the book. There are 2 forces that are pushing up on it. The book has not left contact with the table, so there is a normal force, and there's going to be a force of tension from the string pulling up. And the sum of those 2 upwards forces, support force N and tension T, equals the weight. So I add up all 3 of those vectors together and I get 0. How do the forces exerted on the book, in this case, compare to the forces exerted on the book when the string is not present? So weight is the same either way. The normal force is going to be weaker, and the tension didn't exist before, so the tension is stronger. So forces that are the same would be the weight, and the ones that change are going to be tension and normal force. Consider the following statement made by a student about a book at rest on a level table. The 2 forces exerted on the book are the normal force directed up and the weight of the book directed down. Great, I agree with that. These are equal and opposite to one another. Correct. The book is not jumping up in the air. It's not falling through the table. By Newton's third law, they are a third law force pair. So the normal force is always equal to the weight of the book. That last sentence is very, very, very wrong. Because those cannot be an interaction pair. They cannot be force partners in terms of the Newton's third law of motion, because you're talking about forces on 3 different objects. Okay? The normal force, the interaction partners are book and the table. And for weight of the book, interaction partners are the book and all of the earth. So those are 3 different things: book, table, book, earth. It cannot be an action-reaction pair. All right, consider a book on top of a level table while the book is being pressed straight down by a hand. In the space below, draw a free body diagram for the book. Label the forces as you did in the tutorial forces. All right, so now I've got the weight of the book down. There is a force from my hand down, and there is a normal force from the table up. And I add all those three vectors together. They have to sum to 0 because the book is going to begin and remain at rest. How do the forces exerted on the book in this case compare to the forces exerted on the book when the hand is not pushing? List any forces that are the same. In both cases, make a separate list of forces that change when the hand is pressing down on the book. Okay. So the weight of the book is the same whether you're pushing on it or not. But obviously, the force of the push is going to change, and the support force that the table exerts up on the book is going to change to be different from the weight. So same, mg, and the ones that change, I picked my variables to be n table and the force of the push, F sub push. Is the magnitude of the weight of the book equal to the magnitude of the normal force exerted by the table on the book? No. We'll look at our free body diagram. So from our FBD, the support force from the table is bigger than the weight, because the support force from the table has to cancel out the weight of the book and the force of the push. All right. Page 32. Review your answers to Part A. In addition, read the portion of your physics text that discusses Newton's third law. Okay, that's good reading. Then consider a book on a level table. Which force completes the Newton's third law, or action-reaction force pair, with the normal force exerted on the book by the table? And that would be the normal force of book pushing down on the table. So those two forces are equal and opposite. The normal force of the table pushing up on the book is equal and opposite to the normal force of the book pushing down on the table. Those two are always going to have to be equal and opposite. If one were to change, the other one instantaneously changes. Which force completes Newton's third law, or action-reaction force pair, with the weight of the book? That is the force of the book's gravity pulling up on all of our planet Earth. So, what are equal and opposite about weight? The force of Earth's gravity pulling down on the book is equal and opposite to the force of the book's gravity pulling up on Earth. So interaction pairs are always going to be of the form F of A on B is equal and opposite to the force of B on A. We write it out as a vector. The force of A on B is minus F B on A. All right, 3. A chain is suspended by a rope as shown at right. The chain is composed of 4 identical links and does not move. There's our magic words again. Begins and remains at rest. So we are in the regime of Newton's first law of motion, sum of forces equals 0. In the spaces below, draw a free body diagram for each of the 4 links. Label each of the forces as you are instructed in the tutorial forces. All right. So let's start with the bottom link first. It'll be easier. there is the weight of the link down, and that link begins and remains at rest, so there is a force of tension pulling up that cancels out the weight. So we have link 4 begins and remains at rest. Let's look at link 3. It is being pulled up by link 2, being pulled down by link 4, and it has its own weight. So there are 3 forces on it. Link 3 has its weight, which is identical because they're identical links. There is a force minus T4. That's the interaction partner. So link 4 pulls down on 3 just as hard as link 3 pulls up on 4. And we're going to have a arrow just big enough to cancel out these 2 forces. I'm going to call that tension 3. All right. So now we have link 2 begins and remains at rest. Link 3 begins and remains at rest. Let's look at link 2. Link 2 has a force of gravity down. It is being pulled down by link 3, being pulled up by link 1. So force of gravity down, and that is not changing. This vector should be the same size and direction in all 3 of these so far, and all 4 of them in a little bit, because the links are identical. So 2 is pulling up on 3, so 3 is pulling down on 2. So I have a force minus T3. And then what is canceling out those 2 forces? It is tension 2 pulling up. So all of those 3 forces sum to 0. All right. Link 1. Link 1 has its own weight. So there's mg pointed down, and it is pulled down by link 2. So I've got this vector minus T2. And then what cancels that out is tension from the rope. And that is the tension from the rope. All right, part B. Identify all of the Newton's third law action-reaction force pairs in your diagram by placing one or more small cross symbols through each member of the pair, i.e., mark each member of the first pair with 1 cross, each member of the second pair with 2 crosses, etc., etc. Okay. T2 and minus T2, those are an action-reaction pair. Those are going to cancel out in pairs if these are together in a system, because internal forces cancel in pairs. We'll see that here in a little bit. Minus T3 and T3, that is an action-reaction pair. Okay, so T3 is pulling up on 3 and down on 2. T2 was pulling up on 2 and down on 1. And then we've got interaction between link 3 and link 4. T4 is pulling up on link 4. 1, 2, 3 little x's, and down on link 3. 1, 2, 3 little x's. All right. Rank from tallest to smallest, largest to smallest, the magnitudes of all of the forces on your diagrams. Explain your reasoning, including how you use Newton's second and third laws. All right. Well, I'm just going to look at our free body diagrams. That's what we draw them for. So which force is the tallest of allest? Well, it's the tension of the rope. That is the largest force. That is bigger than the next largest force, is T2, which is bigger than the next largest force, T3, which is bigger than the next largest force, T4, and T4 in magnitude is just as big as the weight of a link, which is mg. All right. What's next? I'm going to think a little bit about systems. Let S1, 2, system 1 and 2 together represent the system consisting of links 1 and 2 of the chain in problem 3. So we're going to treat links 1 and 2 as a single object. Draw and label a free body diagram for the system S1, 2. All right, so that is going to have a force due to weight of 2 mg down. The dot is going to be my system, S1, 2. I'm going to have the tension from link 3 pulling down. And for that system, what pulls up on it is the tension in the rope. And system 1, 2 begins and remains at rest. Oh, and I call this minus T3. All right, begins and remains at rest, so I add those three vectors together and they're going to sum to 0. Compare the forces that appear on your free body diagram for system S1, 2 to those that appear on your diagrams for links 1 and 2 in problem 3. So, short version is tension from the rope is the same. This tension down is going to be the same as the tension down on link 2 if it were not the system of the two links together. And then the weight is doubled because it's two links together. So for each of the forces that appear on your diagram for system S1, 2, list the corresponding force or forces on your diagrams for link 1 and 2. So T rope is the same, tension in the rope, minus T3 is still minus T3. And we now have 2 mg is, and that is just mg plus mg. And that's because we have two links together, or system S1, 2. Are there any forces on your diagrams for links 1 and 2 that you do not list? There sure are. If so, what characteristic do these forces have in common that none of the others share? So we have a T2 and a minus T2 cancel out. They are interaction partners, and they will cancel in pairs when both are internal to the same system. So internal forces cancel in pairs. It's one of the beauties and simplifications for Newton's third law of motion. All right, let C represent the system consisting of the whole chain, all 4 links. Draw and label a free body diagram for C. Make sure that your diagram is consistent with the reasoning you used in part B. So if my system is just the entire rope, the entire chain, all 4 links, I'm going to have a force of 4 mg down, and the only force that we have left is going to be the tension in the rope pulling up, and those 2 arrows cancel out. So that is telling me tension 2, tension 3, tension 4, all internal forces system C, and they will cancel out. All right. Now let's think a little bit about inclined planes. We have a block at rest, and the inclined plane shown below at right. A hand pushes vertically downward with a constant force. The block remains at rest on the incline. Begins and remains at rest. So again, Newton's first law of motion, net force on the block is 0. Free body diagram for the block. I'm going to have the weight of the block has to act straight down. There is going to be a force from the hand pushing straight down. There is going to be a normal force from the inclined plane on the block, prevents the block from falling through the inclined plane. And then I'm going to need a force of static friction parallel to the interface between the block and the inclined plane. Force of static friction, and this arrow is just big enough to cancel out the component of the weight and the hand force that are parallel to the inclined plane. Let me just remind you of this angle is theta. This angle is also theta. All right. In the space provided above, draw a free body diagram for the block, label the forces as you did. Okay. For each force that appears on your free body diagram, identify the corresponding force that completes Newton's third law, action-reaction force pair. All right, so I have 1, 2, 3, 4 forces. So we're going to have to identify 4 interaction partners. Partner to the force of static friction, partner to the normal force of the inclined plane on the block. So both of these are forces of the inclined plane on the block. This is parallel to the interface. This is perpendicular. We have the force, the weight of the block, and we have a force from the hand pushing straight down on the block. So the interaction partner to the force of static friction pushing up on the block is the force of block pushing parallel and down the incline through static friction. Reaction partner to the normal force is going to be the force of the block pushing perpendicular into the incline. All right, so out of that contact force between the block and the incline, we're going to have part that is parallel and part that's perpendicular to the interface. Interaction partner to the weight of the block is the force of the block's gravity pulling up on Earth. So now this is the one where the block is interacting with the Earth. These two are both the block interacting with the incline. And now we're going to have the block interacting with the hand. So the force of the hand pushing down on the block is going to be equal and opposite, always, to the force of the block up on hand. All right. Suppose the hand were to push with a constant force directed as shown at right. The block remains at rest on the incline. So we still have some of the forces equals 0. So instead of being straight down, we're going to have the hand pushing perpendicular to the interface between the block and the incline. Is the magnitude of the net force on the block greater than, less than, or equal to the magnitude of the net force on the block in part A? Equal to, because sum of the forces is still 0. 0 equals 0. All right. Is the magnitude of the frictional force exerted on the block by the incline greater than, less than, or equal to the magnitude of the frictional force exerted on the block by the incline in part A? Explain. All right. So let's try to draw our free body diagram to answer this. So the weight of the block hasn't changed. Still have mg. And now there is going to be a force of the hand that is perpendicular to the inclined plane. I'm going to have a normal force that cancels out the force from the hand plus part of the weight, the part that is along here, and the perpendicular component of the weight is all that has to be canceled out by the force of static friction. So in this case, I had to cancel out all of this. It's partly the force from the hand and partly the weight. Now the normal force is canceling out all of the force from the hand, and the force of static friction is going to cancel out just part of the weight. So if you push perpendicular to the inclined plane, then the force of static friction required for the block to begin to remain at rest is smaller. All right. Now one of my favorite free body diagrams. I am pushing a book into a wall. This is no different really than pushing a book into the table, which we already did, but this one always bends people's noodles, so let's think through this. Person pushes a book against a wall so that the book does not move. All right, does not move. Sum of forces equals 0. Newton's first law of motion. Draw a free body diagram for the book. Label the forces as you did in the tutorial forces. Okay. The weight of the book is down. I am pushing the book into the wall with a force from a hand. I'm going to call that a push, force of a push. The wall is going to push back with a support force to prevent the book from going through the wall. If I were more careful, those two arrows would be equal and opposite. So those two cancel out. So what cancels out the weight? It can't be the force from the push because that has no projection down. It can't be the support force from the wall because that has no projection down. What cancels out the weight of the book is a force of static friction. All right. For each force that appears on a free body diagram, identify the corresponding force that completes Newton's third law, or action force pair. All right, so what's equal and opposite to the normal force from the wall in the book? What is equal and opposite to the force of static friction on the book? What is equal and opposite to the force of the hand pushing on the book? And what is equal and opposite to the weight of the book? All right, so the force of the wall pushing the book to the left is equal and opposite to the force of book pushing wall to the right. what is equal and opposite to the force of static friction pushing up on the book is going to be the force of static friction pushing down on the wall. Equal and opposite to the force of the hand pushing the book to the right is going to be equal and opposite to the force of book pushing hand to the left. Alright, and equal and opposite to the weight of the book. So the weight of the book is the force of Earth's gravity pulling the book down. That's going to be equal and opposite to the force of the book's gravity pulling Earth up. There we go.